Alright, so today we're finally getting into actual Lie group talk. I've kind of looked through various discussions and kind of debilitated myself how to go over everything. I think what I'm going to do, I wrote down my plan before, but I think we're going to go through a brief discussion with Sarah and then go back and recover everything through Bourbaki. So there might be a bit of repetition at one point, but I feel like their topics are pretty disjoint from my brief scan through, so hopefully this should work out pretty well. And so this chapter title is actually going to be Analytic Groups, which is just Lie groups. And throughout, we let K be a field complete with respect to a non-trivial absolute value. And so first off, we ought to define what a Lie group is. Definition of analytic groups. So let G be a topological group, which is just a group with a topological structure. And it's also, in this case, going to be an analytic manifold over K. Then G is said to be an analytic group or, more funly, a Lie group over K if, first off, the map from X and Y to their pair of G times G into G is a morphism. And secondly, the map from an element to its inverse of G into G is a morphism. So essentially, if you think about the defining characteristics of a group, we just need that all to align with the manifold structure, as you would expect. Because like, what do we need for a group? We need associativity of our function, which isn't really going to have a topological consequence. There's our product itself is going to be there. It has to have an inverse. Having an identity is trivially going to be a morphism. It's going to be the identity morphism. So that's all of our defining characteristics, I think, right there. So, quick remarks. Okay, first off, suppose G is a Lie group. And then, first off, G has to be Hausdorff. Secondly, it has to be metrizable. And thirdly, G is complete for the left or right uniform structures. I'll write this as a theorem. It has this remark, but it's structured like a theorem. I think theorems are cooler, so we're just gonna pretend this is a theorem. And our proof here for A, since we know from previous texts that a topological group is Hausdorff if and only if the intersection of identities of neighborhoods of the identity is just the identity itself. Which makes sense. I mean, that's kind of like any other point. You have essentially you have the Hausdorff condition at essentially it's saying for the identity you have the Hausdorff condition at that identity, and then by a group structure, of course, you can move those anywhere you want. So it should be pretty intuitive to see. And this holds since G is locally isomorphic to an open subset of k to the n for some dimension n, our metrizability comes from G being Hausdorff, and we know that E has, I'm mixing up my tenses here, as E has a denumerable fundamental system of neighborhoods, which is also by a text that we don't have access to. And for condition 3, we look at the right uniform structure. By symmetry, showing there is a neighborhood we're going to call V of the identity which is complete in the induced uniform structure. As follows. So we're going to let U phi n be a chart at E such that it sends E to 0, and we're going to let V1 be a neighborhood of E such that the element of V1 times another element of V1 is always going to be inside of the domain of our chart. And then the law of composition on V1 is induced via phi from an analytic map f from phi of v1 times itself onto phi of u. For some y bar in the image of phi of v1, f of y bar comma 0 minus f of 0 comma 0 is equal to y bar minus 0, which is going to just be y bar. Oops. Then, since f is analytic, there is a closed neighborhood v of e in v1 such that for y bar comma x bar in phi of v times phi of v, we have that, I'm going to write this on a new line, half of the size of y bar is bounded by f of y bar comma x bar minus f of 0 and x bar, which is at most going to be 2 times y bar. Now we show that V is complete by showing that its uniform structure agrees with the uniform structure induced by phi from the uniform structure on phi of v by the additive structure on k to the n. Now, a fundamental system of entourages of the uniform structure of V given by sets of the form VW contained in V times V, where they don't even complete the sentence. I don't understand what's happening with that, but W is a neighborhood of E and V And phi of w is a ball of radius epsilon around 0. Secondly, v of w is given by the set of w on x times x for x in v, w in w, w and w times x still being in v. Now, we're going to let n delta be the set of y bar and x bar in phi v times phi v, where the distance between y bar and x bar is at most delta, for delta being strictly positive, of course. These sets and delta form a fundamental system of entourages. Oh, new page. For the uniform structure on phi of v induced by the additive structure of k to the n, with w as above, we have that we can put phi times phi on our VW between n of epsilon over 2 and n of 2 epsilon. So the two uniform structures on V, demonstrated structures, agree. Since the uniform structure induced by the additive structure of k to the n is complete, as V is closed, we are done. And this shows that the left-right uniform structures locally agree with the uniform structures induced by the charts. Okay. We have another theorem, another remark which I'm going to write as a theorem. This is regarding our two axioms way up above, what they call axioms. Where axiom 1 is that the product isomorphism, axiom 2 is that an inverse isomorphism. So part A says that axiom 1 implies that the map setting y to x, y is the map of left multiplication by x is an isomorphism for the manifold structure of G for a fixed x. Second is that our axiom system is actually redundant. Axiom 1 implies axiom 2, essentially if products are a manifold or an isomorphism, inverses have to be as well. Wait, we don't have that they're isomorphisms, do we? That doesn't make sense. We have that they're morphisms. Yeah, the product being a morphism implies that the inverse is a morphism, and we actually have that axiom 2 implies that the map from it, the inverse map, is not just a morphism, but it's actually an isomorphism. Pretty exciting. So for proof, we want to do a bit of setup first. Let phi be the map from g squared to g times g to g by x, y. This is just our product. We're going to let phi of x be left multiplication by x. And this is going to be map setting y to x times y. And let psi be the map from g to g, bx to x inverse. Let t1 phi and t2 phi be the first and second partial derivatives of phi. And our part A is that essentially saying that phi x is an isomorphism is by the fact that phi x is the composite of the map sending element y and g to x and y I guess this is going to be a map from g to g times g. And then secondly, we're going to apply our standard multiplication. And the fact that phi x has an inverse, which is just phi of x inverse. It's worth noting that ty of phi x, mapping the tangent space at y of g into the tangent space at xy of g, may be identified with the t squared, the second partial derivative of xy at xy of phi, sending ty of g into txy of g. That's a 6, not a g. With t squared of phi being an isomorphism. Part B, show that multiplication being a morphism implies that inverses are morphisms. So we're going to let, first off, we're going to let theta be a map from g times g into g times g as theta of x and y, just be multiplying the element on the right by the element on the left, so x to xy, which is, we can rewrite with our explicit multiplication as phi. Then theta is bijective and étal at each point xy of g times g, which we see by seeing that at x times y t of theta has the form t theta is going to be t of the identity of g, y is going to be, y of x is going to be 0, x of y is going to be the first partial derivative of phi, and then our second partial derivative of phi. So t theta is an isomorphism. So theta is an isomorphism. We're going to let sigma be the inverse of theta, which is of course just going to be xy into x comma x inverse of y times y. Then sigma of x and e is going to be x and its inverse, which is x times, of course, we can write inverse using c of x, and this holds true for all x and g. So phi is a morphism. Part C, which was that our inverse map is actually an isomorphism, which is just by that phi squared is 1, so phi has an inverse. Alright, and that's our first section. How long has it been? 30 minutes. So our next chapter is on examples of linear groups. I'll give at least one here, and then we might leave the other examples for next time. So, elementary examples of analytic groups, which I'm going to be writing as Lie groups to emphasize this is a Lie course, meant to be. So first off is general linear groups. So this should be familiar overall. Let R be an associative algebra with unit and be finite dimensional over K. The general linear group over R is the group, which here we're going to write as GM. No, I'm going to write it as GLM of R of invertible elements of R. Then we are going to see that the general linear group over R is a Lie group open as a subset of R. And you may recall my earlier discussion at the very start of correspondence between Lie groups and Lie algebras. This should correspond to the set of matrices with a zero trace as the algebra. So first we're going to show, we can show as open by showing there is a neighborhood of the identity in GLM of R. Now, we know there exists an open neighborhood U of 0 in R such that for x in U, the sum of x to all natural numbers converges. Then V being essentially 1 minus actually. 1 minus U, 1 plus U, I don't think it matters. 1 minus the elements of U in GM in the general linear Lie group of R is a neighborhood of 1. GLMR is a Lie group, Then as multiplication is a morphism as it is bilinear in R. Oh, okay. Once again, my foolishness has brought problems. This should just be G, because the GL is actually a slight, bit of a special case. That's why you don't listen to me until I get to the end here. Yeah. So, when R is the endomorphism ring, and V of a finite dimensional vector space, V over K we call GM of R the general linear group of V as GLV. When V is n copies of K, we write it in the form I was alluding to. GL of V is equal to, you can either write it as GLN comma K, which is honestly kind of lame, or the better GL sub n of K. Which can be identified with a subset of the set of n by n matrices of K, where they're going to be invertible, of course. Now, here's where we get to the fun stuff. Suppose that K is ultrametric with evaluation ring A. Then for alpha as a matrix with components I, J, in GLN of K, the following are equivalent. First off, we can say that A defines an automorphism of n copies of our valuation ring on just K itself. It's equivalent to, first off, each alpha ij lies in the valuation ring. Each component of our matrix form of alpha lies in the valuation ring. And the determinant of alpha is a unit in alpha. Now, we can let GLN of A denote the set of alphas in GLN of K satisfying the above conditions. Then, by condition 2, we have that the general linear Lie group, the GLN of A, is both closed and open in the endomorphisms of K to the n. By 1, GLN of A is a group and so is a Lie group. Which we're of course going to call the general linear group of n by n matrices over A. Now, finally, suppose the K is locally compact. Then the GLN of A generally Lie group over A is a compact and open subgroup of the n by n matrices on K. Later we will show this is our theorem, which we're not going to prove until a later video, stating that the GLN of A is a maximal compact subgroup of GLN K, and if G is a maximal compact subgroup of GLN of K, then G is a conjugate of GLN of A. But we're not going to be showing this until we are a bit more comfortable with groups. And yeah, next time we'll be looking at a couple more examples of groups, then potentially moving on to some other, constructions and that in groups. So look forward to that. Yeah, thanks for watching.